Hi everyone. So this is the fifth video in the AVL tree series. And in this video, what I want to do is I want to show why rotations actually work. Like so far in all the examples, they seem to work, but is there a way to prove that they actually do work when we apply them? So before we start, I want to first look at what a rotation does to our tree. First of all, to show that a rotation is never harmful. And what I mean by that is that uh, we started off with a binary search tree before the rotation. By doing the rotation, I want to show that at the end of it, we still have a binary search tree. Okay. Now, and so let's start with that idea. Does a rotation ever cause a binary search tree to become invalid? So in the case of a binary search tree, what we do know about it is that the way that values are arranged is based on comparing the values within a subtree against a node, right? So for example, if I look at this diagram here, everything in the subtree X, every single value here, it has to be less than A because it is to the left-hand side of A, right? So what I know about the initial subtree is that X, everything in that subtree, must be smaller than A. Now, by the same idea, I know that everything in the subtree B, that's B and actually everything in Y and Z, we already know that all of it is definitely bigger than A. Otherwise, it wouldn't be to the right of A. Now, furthermore, what I can also say is that Y over here, which is to the left of B, is both smaller than B, but also bigger than A, and is bigger than A because it's to the right of A still, right? So it's a subtree of B, B is to the right of A, so Y is bigger than A, smaller than B. Similarly, Z must be bigger than B because it's to B's right. So that's the idea in terms of where values are with respect to each other in this particular tree. Now, when the rotation finishes, the values have to be in trees where this inequality holds. This expression has to hold throughout. So if we look at this tree, X is still smaller than A, because it is to the left. Y is bigger than A because it's to A's right. Now B has to be bigger than A because it's A is to B's left, right? So A must be smaller than B. And finally, Z must be bigger than B. So what we have is we have the inequality for A, B, X, Y, Z. They're the same in the two trees. So doing a rotation doesn't cause this to become to be an error. Okay, so in other words, before I started, I had a binary search tree. After I'm finished, I still have a binary search tree. So this is good. This is exactly what we want. So now what we want to do is we want to take a look at um, why does a rotation fix our height problems? So we're going to start off with a single rotation. So this is done. Remember, we do the single rotation if the signs are the same. So +2, +1, okay? Now, I'm only going to do this one rotation. The other version where you do, you know, -2, -1, the other single rotation, it's just a mirror image. So the reasoning behind it is done exactly the same way. Feel free to look at it on your own. Now, I'm going to start off by taking a look at how tall these trees are. Now, because this is a very general thing, I can't actually say, oh, X is 5 nodes tall. We don't know how big X is. Um, so what we're going to do is we're going to represent the height of X with the letter H. So H is how tall X is. Now, what do we know about the height of X? We know that it can't be negative. That's all we know, okay? So we know that H must be greater than or equal to 0, okay? It can't be less than 0 because that doesn't make any sense. we've seen trees of height 0 in that position in our examples. So we know 0, it can be 0. It could also be a positive number, 1, 2, 3, 4, whatever. But let's call that number h, okay, whatever that may be. Now, other than that it's bigger than 0, what else do we know about h? Now, we don't know what h is, but we do know how tall everything else is based on h at this point. Now we can actually figure this out. So how do we figure it out? Now, for example, this one right here, B. How tall is B? Well, uh, we remember that this number here, the +2, we obtain this number by taking the height of B and subtracting the height of X, right? So if we took the height of Z and we subtracted the height of X from it, what we end up with is +2, okay? Now, at this point, we actually know what the height of X is. It's little h. So I can substitute that in. Now, if we solve for hz, hz, my bad, sorry, this is hb, the height of b. The height of b minus the height of x gives you +2. That's how this balanced value came about, okay? So the height of b is this arrow that I've highlighted in green here. That's the height of b. And if I take the height of b and I subtract the height of x, I get +2. So height of b minus h gives me +2. Now, what is the height of b then? Well, the height of b is simply h +2. We're just solving for hb here. So what I can say here is that the height of the entire tree that starts at b is little h +2. Whatever the height of x is, add 2 to it, that's the height of b. Okay? And that's strictly from the way the balancing works. So that is the first part of that equation. Okay? Now, what else do we know? Now, between uh, y and z, z is the taller tree. How do I know that z is taller? Because this thing is +1. Remember, the positive means the right-hand side is taller. Now, if you have a tree and one side is taller than the other side, the side that is taller is the one that contributes to the height of the entire tree. So what I mean by that is that if I have a node here and this side has 2 nodes, so this subtree has 2 nodes, and this subtree only has 1 node, so 2 nodes tall, I should say, the height of 2, whereas this one only has a height of 1. What will happen is that the tree on the right pretty much lifts up the entire tree. So the height of the entire tree is the height of the taller child, the taller subtree, +1. So the height of this whole tree will be 3 because it's the taller tree's height, and then you add the root node to it, so it's 1 taller, so it's 3. So what this means is that between y and z, Z is the thing that lifts up this tree to form a height of h +2. It also means that Z's height is B's height minus B itself. So the height of B is h +2. But if we don't count this node B, then the height will be the height of Z. So hz is equal to the height of B minus 1. Okay? So what is the height of B? The height of b is little h +2. And if we subtract 1 from it, what we end up with is little h +1. So the height of z will be whatever h is +1. Okay? And we get that idea because z is the taller tree, so it is 1 shorter than the subtree starting at its parent. That's what it is. So that's how you get hz. Now, what about the height of y then? Well, remember, this plus 1 comes from the fact that we took the height of the right, and then we subtract the height of the left, right? So what we know is that hy is, if we took, um, sorry, if we took hz and we subtracted hy, what we're going to get is plus 1. Now, we know that hz is little h plus 1, so we can substitute that in. Sorry, it's equal to plus 1. Okay, and so if we solve for hy, what we end up with is hy is equal to little h plus 1 minus 1, which means that this whole thing is h. Okay, so little y over here is h. Okay, and this is just some algebra manipulations, but that's where we get this from. Now, why do I want to know how tall x, y, and z are? The reason is because they don't change. So x before and after the rotation is exactly the same tree, same with y and z. So what that means is that when the rotation is finished, little the x subtree is still h nodes tall. The y subtree, likewise, is also still h nodes tall. And the Z tree over here, this is now h plus 1 tall, same as it was before we did the rotation. So because the trees don't change, their heights are exactly what they were before you do the rotation. Now, so if we use this principle, then what we know is that the height of the entire A tree, okay, is the taller child. Now they're the same height, plus 1 more node for A. So the height of A will be h plus 1. Okay. Now, what does this mean? Well, so first of all, the balance of A will be 0 because the height of its right subtree is h. We subtract h, and we end up with 0. Now for b, the height of b is going to be, well, height of b is h plus 2. But more importantly, the balance will be the height of its right subtree, which is h plus 1. And then we subtract h plus 1 from that. And what we end up with is 0, because we're just taking two numbers and subtracting the same number from each other. So we're at 0. So what I've shown here is that if you have a situation like this, where this is plus 2 and this is plus 1, then doing a rotation will completely fix the balance situation. Okay, and remember, x, y, and z were already balanced, so we don't have to worry about those guys. We don't do a rotation from the top down. We always do it from the bottom up. If there was a problem, we would have fixed it already before it got to the point where we actually get to the node A. Okay, so that is why a single rotation works. Now, on the same principle, we can show that a double rotation also works. So here's a diagram of a double rotation. Now, first of all, let's make sure that our inequality holds with a double rotation. Now, a double rotation involves more trees and more subtrees, but we actually still have the same sort of relationship. Okay, now if we start with W, we know that W is to the left of A, so W is smaller than A. Everything in B, so everything else, is definitely bigger than A. We know that. Now Z is bigger than B. What about C, X, and Y? Now, all of it, X, Y, and X, Y, and C are all to the left-hand side of B, right? So that means that C is definitely smaller than B, but it's also definitely bigger than A because it's still in the right subtree of A. Now X is smaller than C, so X will be here. while y will be bigger than c, but all of this is smaller than b. So this is the relationship we have when we look at the diagram before we started. Now, after we're done, do we still have the same do we still have the same organized, do we still have the same relationships? And the answer is yes. Okay, so w is still smaller than a, x is bigger than a. Okay, c is bigger than everything here, so we can put c next. B and everything underneath it is bigger than c. Y is bigger than c but smaller than b. And z is bigger than b. Now, that's just based on where they are positioned relative to each other. Now, if we take a look at the inequality before and the inequality after, it's the same expression. So we can say that this is true, this is the same, this is the same. So we don't have to worry that the rotation does anything bad to our tree. We still have a binary search tree when we do a rotation, when we do a double rotation, okay? So that's good. Now, we're going to use the same principle that we used earlier to figure out how tall everything is. But this one is a little bit more complicated. And it's a little bit more complicated mostly because we actually don't know what C's balance is. We don't, and that's okay. We can actually work with this even though we don't know what this is. Now, what we do know is that C's balance, okay, C's initial balance, uh, C's initial balance is definitely plus or minus one, plus one, minus one, or zero. We don't know what it is, but we know it's one of those three. And the reason why it is because we always fix our tree from the bottom up. If this wasn't plus minus one or zero, we would have fixed it already. And then it would have been zero, right? Or plus one or minus one, right? So if there was a problem here, we would have already fixed it. So there's no reason that we have to worry that it will be something other than these three. It will always be one of those three values. So the question is simply if it's different, then what happens? Okay. So now let's take a look at the problem the same way that we did before. Okay. W is going to be given an initial height of h. We don't know what h is, but just like before, we do know it is greater than or equal to 0. So h we know is greater than or equal to 0, just like with the first tree, same reasoning. Okay, we can't have a negative value on h, but we can have an empty tree. Now, how tall is everything relative to w then? Okay, how tall is everything relative to w's height, I should say. So um, now, again, just like before, we can say that the height of b minus the height of w is going to be equal to positive 2. And the reason, of course, is because the balance at A is positive 2. So whatever height B is, and that's the whole thing, including all of this stuff, right? The height of B, that's this thing right here, height of B. We don't know what it is, but we do know that it is 2 taller than whatever W is. Now, W is H, so HB minus H gives me plus 2. Solve for HB, and what we end up with is h plus 2. Okay, so what we can say is that the height of B is 2. Sorry, not 2, my bad. Sorry. The height of B is h, little h plus 2. Okay, so that's the height of B. Now, so if B is h plus 2 tall, now at this point, who is the taller of B's subtree? So in this case, B has a value, a balance value of minus 1. Remember, we only do this if we have if the signs are different. That's why if this is plus 2, this has to be minus 1 for us to be using a double rotation. So if B's balance here is -1, then C, this tree right here, all of C, is the taller of the two children. So what this means is that C, the tree C, the entire C tree, is the thing that holds up the B node, okay? So what we know is that the height of B is equal to the height of C plus one more node for B. Okay, so however tall C is, add one node for B, that is the height of B. Now, we know that the height of B is h plus 2, right? So, therefore, what is the height of C going to be? Okay, so that's what this is. So solve the equation, and what you end up with is HC is actually equal to little h plus 1. Okay, this is just solving the equation for h height of C. So the height of C is h plus 1 tall. The entire tree is h plus 1. That's what we know about it. Now, um, because of this, what we can also do now is we can actually find the height of Z. That's the easy one to do. So HZ plus HC, okay, we know that the height of Z, or sorry, HZ, if we were to subtract the height of C from it, what we will end up with is -1. Okay, so this formula here, of course, comes from this value. This is calculated by taking the height of Z and subtracting the height of C from it. Now we know that the height of C is h plus 1. Okay, so that's the equation. So if we solve for hz, what we end up with is we're going to end up with h. Okay, so so the height of Z is h. In other words, Z and W are exactly the same height. Now, that's good. So the only thing left to do is to figure out what X and Y are, how tall they are. Now, the good news is that X and Y's height um, cannot, so first of all, they can't be negative, okay? So none of these can be negative. The height, one of them has to be h units tall or h nodes tall, okay? One of A and B, or sorry, one of X and Y must have height h. That's what I do know for sure. And the reason it has to have a height of h is because the entire tree is h plus 1 tall. So the plus 1 is for the C node. So the rest of the height must come from either x or y. Okay, so one of them has to hold up the C to a height of h plus 1. So maybe it might not be both, but one of them has to have a height of h. Now, let's take a look at the different possibilities, because at the end, that's really what it comes down to. Like, what are the possible heights for x and y? And when it comes down to it, we can sort of do this in a chart form. Okay, so if we take a look at the possible, the possible balance of C. Okay, C has three possible balance it can be: -1, +1, and 0. Okay, it can't be anything else because it had to have been fixed before we got to this point. Now, what is the height of X? What is the height of Y if for each of the balances? Okay, so imagine that C's balance was labeled as +1. That means that Y is one node taller than X. Now, remember, the taller tree is the one that has to hold up everything. So what this means is that in this case, oh, sorry, I'm drawing this in backwards order. I started with +1. So this is H, So if when it's plus 1, y is the taller tree, so y must be h. Now x has to be shorter, so it has to be h minus 1. So even though we allow h to be 0, it can't be 0 if this is plus 1. Okay, that's actually because otherwise we would end up with like 0 minus 1 here, right? So we can't do that. Now, what if this was minus 1? Well, if it's minus 1, then the height of x is h, but the height of y will be h minus 1 to sort of make it the other height, to make it correct with both balances and height. Now, what if C has a balance of 0? If C has a balance of 0, they're equal in height. So both of them have to hold up C, so they're both H. So this is pretty much what it will be when it comes down to it. So X and Y, one of them is allowed to be H minus 1, but at least one of them will be H. Okay? So, okay, so now that we have that, let's take a look at what we have when we're finished. How tall are each of the trees? Now remember that the heights of the trees do not change after the rotation. So W has a height of h before, it has a height of h after. Z has a height of h before, it also has a height of h after. The only question is, what about x and y? Now, what we do know is that x and y is either h or h minus 1. It can't be anything else. So that means that either it is the same height, for example, as w, and therefore um, they end up both hold up the a tree. So in other words, like this one, a is going to have a height of h plus 1. Okay. Now, what if it wasn't h? What if it was h minus 1? Well, that's okay because w is already holding up the a tree to a height of h plus 1, right? So we didn't need x. We only needed w to be h tall. So similarly, what we know about b's height is that no matter what x and y is, oops, the height of b is going to be h plus 1. So what this means is that we can be certain that the balance at C when we're all done will definitely be 0. Now, what about the balances of A and B? Well, those might be different. It depends on what C was beforehand. Okay, so balance of A, balance of B. Okay, so the balance of A, if if x had been h minus 1 and y was h, okay, that's what the first row says. If that was the case, then the balance of A is going to be minus 1 and the balance of B will be 0. For if C had started out as minus 1, so x was taller, then what that would mean is that we would end up with h over here and h minus 1 over here. So the balance of A would be 0, and the balance of B would be positive 1. Z's taller than Y. Now, if both A and B are H, okay, in other words, the balance of C started at 0, then the balance afterwards is going to be 0 at both A and B. So that's pretty much it. We don't exactly know what the balance at A and B is. We actually have to figure that out depending on the situation. But what we do know for sure is that their balances is going to either be 0 plus 1 or minus 1. That's the important point. They're not off balance when we're done. So that's pretty much it. This shows you that a rotation will A, not change the tree into something that isn't a binary search tree, and B, that it fixes our balance problem. Okay? And that's pretty much it. Okay? So in the next video, we will talk about how to actually code this thing. Okay, so we've talked about why they work. We've drawn tons of pictures. How do we code this thing? Okay, so that's it. See you soon.